Hello everyone! We are Group 6 from SKEE1073 Section 6. In this video, we will demonstrate how to convert an AC circuit into a DC circuit. First of all, you should know that converting AC to DC involves three main stages. They are the rectifier, filter, and regulator. Now, let's talk about the rectifier. The circuit shown on the screen includes 4 diodes. This diode form a full-wave bridge rectifier which converts the AC input voltage into a pulsating DC voltage.
How does it work? Well, during the positive half cycle of the AC input, D1 and D2 conduct current, while D3 and D4 are the reverse bias. Then, during the negative half cycle, D3 and D4 conduct current, while D1 and D2 are reverse bias. So, only two diodes conduct at a time. Next is the filter. Its role is to reduce the variation in the rectified voltage. In our circuit, the filter is simply a capacitor connected between the rectified output and the ground. This helps to smooth out the voltage. The small fluctuation that remain is called a ripple. The ripple factor indicates how effective the filter is. Finally, we added a Zener diode as a voltage regulator. A Zener diode can maintain a constant DC voltage even if the input signal or the load resistor change. In our circuit, we use several additional components including a generator as the AC power supply, one breadboard to connect all components, 2 resistors to help us measure the voltage across the circuit, 3 multimeters and 3 oscilloscopes to observe the voltage value and waveform patterns. Now we will walk you through how we configure the component in the simulator.
We set the function generator frequency to 50 Hz, the amplitude to 9 volt, the offset to 0 volt, and we selected a sine wave as the waveform. The multimeters were set to the voltage mode. A branch rectifier circuit using 4 silicon diodes. The capacitor value was set to 1000 microfarad. The resistor was set to 220 ohms and 1 kilo ohm, and then the Zener diode was set to 5.1 volt.
Now, we will present the simulation result of our circuit using both Tinkercad and LTSpice to analyze and verify our design. Firstly, we use Tinkercad to simulate the basic behavior of our circuit. This platform allows us to quickly test the functionality of our components, such as the rectifier, filter, and voltage regulator in a simplified and visual environment. The first waveform respects the AC input voltage. The second waveform is tagged after the filter capacitor, and the third waveform is a measure after the voltage regulator. However, to obtain more accurate and detailed waveform data, we also simulate the circuit using LTSpice. In LTSpice, we make a few adjustments specific to simulation environments. Notably, we replace the oscilloscope with transformer to emulate the input voltage more effectively. We use a 4-to-1 step-down transformer to generate the appropriate input peak voltage. The rest in our circuit include the rectifier, filter, and voltage regulator use the same component value as in our Tinkercad simulation and theoretical design. Now, let's take a look at the waveform result from LTSpice. Green waveform, this shows the AC input voltage before rectification. Red waveform. This is the voltage after the capacitor filter, where we can observe smooth DC level with some ripple. Blue waveform. This is the regulate DC output, showing a much more stable and constant voltage after passing through the voltage regulator. By comparing one simulation platform, Tinkercad help us verify circuit logic and connectivity, while LTSpace provide a precise waveform analysis to evaluate the performance of each stage.
So we have successfully converted AC to DC using rectifier, filter, and voltage regulator. Thank you for watching our video.